We have seen that the Feynman integrals for loop diagrams are singular, and as I said earlier, that we will have to use a regularization procedure to filter out the ultraviolet singularities. Now this step is not going to not going to solve the problem, because at the end I should remove the regulator, and when I do so, the singularities will be present. Okay, so but nevertheless this is the first step. So let me show you how to do this, and first I will do this in the simplest setting, which means I will not be using Feynman integrals but some ordinary simple integrals, and tell you what the idea is. So we want to regulate the integrals. Okay, suppose you have an integral I, which is integral 2 to infinity dx over x. Okay, so this is going to serve as a toy example for Feynman integrals. Okay, now you see that this integral is singular because upper limit infinity gives you a divergence. This integrates to a log of x, and when you put the upper limit, it gives you a log of infinity. So what I do is I look at a modified integral, which I will call I regulated, which is defined to be 2 to some capital lambda dx over x. This gives you log of lambda minus log of 2. Okay, so here we have regulated the integral. As lambda goes to infinity, you recover back this original integral I, right? So I regulated, I subscript reg goes over to I when you take lambda to infinity. But when you put lambda to be a large number but finite, this is how this singularity appears. So there are two terms. One is finite, so that's the finite contribution, and that's the singular contribution. Okay, singular in the lambda going to infinity limit. Okay, so this is an example of a regulator. I'll give you another example. Again, let's look at the same integral, and I will regulate it differently. So I can regulate by the following method. So I will write it as I prime regulated, which is the following. So I modify the integral to this. This is the original one. From this I subtract okay. Let's see why this will regulate the integral. Lower limit 2 is not a problem. Nothing diverges at x equal to 2. Okay. But when x goes to infinity, this is diverging. Okay. It has 1 over x, and that becomes singular. And the integral of it is also singular. But here what I have done is I have introduced a cutoff m. Okay, m is a large number. M is large. So when x becomes very large, but m is finite. Okay, m is large but finite. Now when x becomes large, very very large compared to m, then the contributions from these regions of large x are same in this integral and this integral, right? So you can effectively drop m when x is very large, and this gives you dx over x. So large x behavior of the integrand is as 1 over x. Okay, and this one also has 1 over x. So you see that you will not get a singularity because of this upper limit. You understand? So large x behavior of the second term integrand is same as the original integrand. Okay, which cancels the singularity arising from x going to infinity. Okay, so having dx 1 over x minus 1 over x plus m, that gives you a regulated integral, and you can explicitly check that I prime regulated is log of 1 plus m over 2. Okay, so now I should take m to infinity. Why? Because when I take m to infinity, then this integral vanishes, right? Because it's 1 over infinity, which is 0. Okay, so this integral just drops out, and you are left with only the original integral which we wanted to determine. Okay, so this is a intermediate procedure where I have regulated the integral, and when I put m going to infinity, this gives you a divergent contribution. Okay, so it's a divergent result, which you already know it should be divergent. But for any finite m but large, this is a finite thing. Okay, so these are kinds of regulators that we use in the Feynman integrals also. So these kinds go by the name of Pauli-Villars, and these ones by momentum cutoff. Okay, this variety where you put a cutoff on the momentum, that is called momentum cutoff, and this where you change the propagators, it's called Pauli-Villars. So maybe I should tell you. So momentum cutoff we have already seen, so I'll just mention Pauli-Villars. So here you will replace the propagator by where m square is a large number which you have to take to infinity at the end. Okay, and the argument I gave before applies. Okay, so these are some regulators that you can use, but the best one to use is dimensional regularization. Okay, and that is what I'm going to talk about now. Dimensional regularization. Which means that I will take a given Feynman integral and reduce the number of dimensions low enough that the integral becomes convergent. Okay, you remember that all these divergences, for example, here in this Euclidean integral, the divergence comes because of these powers in the numerator becoming larger than the denominator or equal to the denominator, powers of L in the denominator. Okay, so but if I reduce this dimension sufficiently, then I can make the integral convergent, okay, or finite. So that is what we do. So we take the number of dimensions to be small enough that the integral is finite, but then I should be able to take the n equal to 4 limit, okay, because all the integrals have to be done in 4 dimensions. But thing is that I should be able to continue continuously these numbers, these dimensions. So I should be able to do to give the expressions of the integrals even for fractional or fractional dimensions. Okay, so what I'm going to show you is that this can be done, meaning we can continue to I'll show you that we can continue the dimensions the dimension n to the complex plane. Okay, and this is what I plan to show you explicitly in this lecture. Okay, let's see how it is done. So we have seen that one loop integral one loop Feynman integrals, they are of this form. Earlier I had written only with x, not two variables, x, not two Feynman parameters x1 and x2, because I had used up the delta function already in writing down the expression. But if you keep the delta function, then you get the following. Okay, so here I have, instead of putting n equal to 4, I have put n, but then n is discrete here. N could be 2, or n could be 3, or n could be 4, or n could be 1, depending on in how many dimensions the given integral converges. Okay, so that's the form of the integral. It depends on all these parameters. The m square depends on all these parameters, and all the momenta that you have, their dot products, and m square. Okay, if you have more than one variety of particle, then you may have different masses here, m1 square, m2 square, and so forth. So this was for a particular example where you had only two propagators, that's why you have a 2 here. And we also saw that multi-loop integrals have exactly the same form, except for the fact that there are few more Feynman parameters that appear. Okay, because you have many more propagators in the problem, but the general structure is identical. So you get dx1, dx, I'm using capital N for the number of propagators. So for each propagator you have a Feynman parameter. Then we saw that it has to be dnl, okay, Euclidean. L is the number of loops. And here I have omitted many other constants because I want to only focus on the relevant integral. Okay, this m square also depends on all these parameters. Let me write xi, pi dot pj, m square, or let's say I allow for different masses, so I write mi square. Okay. Of course, for the theory which we are looking at, there is only one mass, so you don't have a subscript I here, but in general you will have that. Okay, n is the number of Feynman propagators. Pi's are the external momenta, mi's are the masses, L is the number of loops, n is the number of dimensions. Okay, where n we want to we need results for n equal to 4. Okay. So that's the structure. Maybe I should write here n is number of propagators and L is number of loops, n is number of dimensions. Okay, so that's the general structure. So let's look at this K integral, KE integral, because that is the one which gives ultraviolet divergence. So its structure is, it has some powers of k in the numerator and some different power of k in the denominator. So I will concentrate on an integral of this form. So I define I d n m to be the following: d dk e over 2 pi d times 1 over minus k e square minus m square power n. Okay, so here if you are looking at one loop integral, then d is equal to n. Okay, but if you are looking at a multi-loop integral, then d is equal to n times l. Okay, that's the thing here. You have to take care of the factors of I when you go from Minkowski to Euclidean by changing by taking k naught along the along the imaginary axis. So each k naught will bring a factor of I. Okay, here in this case, when you are looking at one loop, you get only one factor of I, so that is what you have to multiply here to convert to Euclidean to Minkowski space. But here you will have more number of factors of I, right? Because you had several loop integrals, L number of them. So you will have L factors of I, the complex I. Okay. But anyhow, let's look at this Euclidean integral and try to see if we can write down the integral in a manner where d is allowed to be complex. Okay, see the way it is written right now, d is integer, right? Because here n is number of dimensions, which we are saying it is discrete. It could be 1, 2 or 3. Okay, l is some number of loops, so n times l is integer. N times l is integer, positive integer. Okay, so at the moment here d is a positive integer. If you look at the way this integral is written. Okay, so let's go ahead with this and see if I can write an form of this integral or an expression for this integral which can be analytically continued to complex d dimensions. Okay, and the simplest way is to do the integral. Okay, let us now evaluate this integral. The result will be, of course, a function of m and d and n, and that is why I have put these labels here in the argument of the integral. So you see that the integrand does not depend on the different components of the vector ke independently. Okay, it only depends on the ke square. So it immediately tells us that we should be using spherical coordinates. They are the most suitable coordinates in this case. So let me introduce that. ke1, first component of the Euclidean k, and second component and so forth. There will be total d components. So instead of using these as the integration variables, I do a change of variables and go to the polar coordinate. The radial coordinate I will call r, and then we will have how many angular variables? D minus 1 angular variables, right? Because we have total d variables here. I should have exactly d variables on the right hand side after the transformation. I have chosen one to be r, then others have to be d minus 1. So these are the angular variables that we should get. Okay, so this is our radial coordinate. And these are our d minus 1 angular variables. Okay, so let's see. How about the measure d ke? That becomes what? R power d minus 1 dr. So you see that you have to have a dr, right? Because you are going to these variables. But then you have to have a factor r power d minus 1, because now this balances the dimensions on the both sides. Okay, if k is of dimension momentum, then r also has to have dimension momentum, and on the left you have d powers of momentum, so it's clear that you should have r power d minus 1. So that together with dr it makes d powers of momentum, and remaining ones are angular variables, and the measure I will write as d omega d minus 1. Okay, so this is the volume element in the angular space. Okay, and this d minus 1 tells you that there are d minus 1 angular variables. This subscript reminds you that you have d minus 1 angular variables. Okay, so the denominator of the integrand, which is minus k Euclidean square minus m square power n, this becomes minus r square minus m square power n. Okay, so there is no angular dependence here. That's why we have used it. Now define r square to be m square rho. Okay, all I am doing is trying to just filter out the m dependence. So when I do that, this becomes minus m square rho minus m square power n, which is minus 1 power n m square power n rho plus 1 power n. Okay, that's good. That's about the integrand. Now let's look at the measure. You can easily see that r power d minus 1 dr is equal to m square rho d minus 2 over 2 m square d rho over 2. Okay, you can check by finding what how dr and d rho are related. This is easy to do. Okay, so now when you plug in this this integrand and r d minus 1 dr in terms of rho, you will get the following. Again, simple algebra, you get the following. Let me write the integral also, it will be useful, easier to see. So substituting whatever we have written on the previous page, we get the following. 1 over 2 pi to the d minus 1 power n into half m square d over 2 minus n times the rho integral, which is d rho power d minus 2 over 2 1 plus rho power minus n times integral d omega d minus 1. Okay, let's look at this factor, this line. Here you can take n to be complex. Nothing stops you from saying that n is complex in this. Okay. How about here? We'll see. And how about, so not just n, also about the d. So d and n you can take complex in this, okay, because you have complex functions are defined if you have m square power some complex number. Okay. Here you have this expression, and then I have d omega d minus 1, where it looks like that d has to be integral because that is the number of variables. Okay, you cannot have fractional number of variables, right? You are looking at a volume integral, angular volume integral, where d is the number of angular variables. So it looks like there is no way we could get an expression in which d could be a complex number. But let's anyway push further and let's see what we get. So first we will evaluate this integral, and it will be useful to have with us some special functions. I will write down here. So you have already studied beta function. So beta of z1, z2, where z1 and z2 are complex. There will be some restrictions on what values are allowed, but this is the general expression. T power z1 minus 1, 1 minus t, z2 minus 1. Okay, that's the definition of beta function. There is another expression, another integral expression representation of the beta function, which is 0 to infinity. Here in the integral is from 0 to 1, but you can also write it as an integral where t runs from 0 to infinity, and the expression is this. And this is useful for us because our integral here in the second line is of this form. Okay, let me give you a few more results which we will use. Beta of z1, z2 is gamma of z1, where gamma is gamma function, gamma z1, gamma z2 divided by gamma of z1 plus z2. Okay, and also gamma function is defined as follows. And there is another form. There are several forms, but this is the one we will use. T goes from 0 to infinity, e to the minus t square, t to the 2z minus 1. Okay, so these results will be useful. I think it will be a good idea to keep them safely at one place. Okay, didn't work. Why? let me try again. Hopefully it will work this. Okay, it did work. Okay, so and I should remove this. Okay, good. Let me check if I made any mistake in writing. Z2 minus 1, the first one is correct. Second one is also correct. Third one is correct. 0 to infinity dt e to the minus t power z minus 1, that's right. And this one is wrong. I have missed a factor of half. And for some reason it doesn't write. Yeah. And why? Okay, some strange behavior. Okay, finally. Okay, good. So, where were we? Yeah, here. A factor of half was missed. Good. Here also. So, now you see that this line, okay, this is just beta of d over 2 n minus d over 2. Okay, you can check it from here. So you say that z1 minus 1 is d minus 2 over 2 and minus n is minus z1 minus z2. Then you figure out what z1 and z2 should be and put it here. So that's beta of d over 2 and n minus d over 2. Now you see that even in this second line now, where you have this row integral, even though we had d and n to be integers originally, I can continue to complex plane because beta is defined in the complex plane, okay, for its arguments. So these capital N and D, they can also be continued to complex plane. Okay, now let's, the only thing that is left is the angular integral. So let's look at that first and then I will combine all the results. Okay, let's see whether that can be done. And here I am going to involve this trick. So I evaluate the following integral. I evaluate the integral, let's call it small I. That's not good. What should I call? let's call it j. Okay, integral j, which is the following: minus infinity to infinity dy1 to dy d plus 1, okay, e to the minus y1 square plus y2 square, so and so forth, to y d plus 1 square. Okay, that's the integral I am interested in evaluating because it will be useful in determining omega d. Okay, I am calculating integral d omega d, and later I will replace d by d minus 1. Okay, so because again you see that the integrand, this exponential, involves only the sum of the squares, so it tells us that I should use angular integrals, and that will be useful. I mean spherical coordinates. In spherical coordinates, I will have dy1 to dy d plus 1 is equal to r power d dr. Okay, you have seen already this kind of thing before, 0 to infinity. Okay, see, if you think of y as having dimensions of length or momentum or whatever, let's say dimensions of length, then these are d plus 1, then the left hand side has dimensions length power d plus 1. And because I am going to involve all other integrals to be angular, the total which are dimensionless, so the entire dimension of length on the left hand side has to be matched by this. So r power d dr, that gives you d plus 1 powers of length. Okay, so that's why you have r d, and then you have e to the minus r square, that's coming from here. Okay, where r is the radial coordinate in d plus 1 dimensions, and you have integral d omega d. Okay, and we are interested in calculating integral d omega d, and that's the trick we are utilizing. So what is j then? I have also, so here times e to the minus y1 square to y d plus 1 square. Now this is correct. Okay, so this is j. J is equal to this, which I have written in this form. Okay, now this is equal to, what is this? This I can evaluate by using this gamma function. Okay, you see I have an integral 0 to infinity dt e to the minus t square 2z minus 1, that is half gamma. Okay, so this gives you half of gamma d plus 1 over 2. Let's check. 2z minus 1 is equal to d. 2z minus 1 is equal to d. So z is equal to d plus 1 over 2. That is why I have put gamma of d plus 1 over 2, because that is what you have here, gamma z. Okay, good. So this times integral d omega d. Nice, but now I should evaluate j in another way, so that I can equate those two results, these two results, and get the expression for d omega d. And the idea is that you look at this integral as d plus 1 integrals repeat, the same integral repeated d plus 1 times. So what you have to do is you write j is equal to integral dy, so you can think of this as dy1 e to the minus y1 square, but then dy2 e to the minus y2 square, that's exactly the same integral as this one. So this is repeated d plus 1 times, right? And what is the value of this integral? The value of this integral here is root pi. Okay, that's the Gaussian integral that gives you root pi power d plus 1, which is same as pi power d plus 1 over 2. Okay, so j is pi power d plus 1 over 2, and j is also half gamma d plus 1 over 2 times integral d omega d. So from this I can just extract integral d omega d, the volume integral, which is 2 pi power d plus 1 half, d plus 1 over 2 over gamma d plus 1 over 2. Now let's check whether this is correct result. But before that, you notice that the moment you have this right hand side, no one can stop you from putting d to be a complex number, because gamma function is defined for a complex number and pi you can raise to some complex value. So the right hand side can be continued to complex values of d. Okay, even though the left hand side can be evaluated only for d integral values, okay, but right hand side is also we can continue to complex plane. So with this we have now written I in terms of these functions which all can be continued to complex d and complex n plane. Okay, but before that, let's test whether this result is correct. So I put d equal to 1, and d equal to 1 means I have only one angular variable, and when I integrate over this, I know what I should get. I should get 2 pi, right? And theta goes from 0 to 2 pi. That's the contribution you get. So let's test whether this is correct. So 2 pi power d is 1, 1 plus 1, 2 over 2 is 1, so that's pi over gamma 1, gamma 1, so gamma n, where n is an integer, is n minus 1 factorial, so that's 0 factorial, which is 1, so it is 2 pi. So that's a correct result. Also let's check for d equal to 2. So you have now two variables, theta and phi. So here you had only one, here you have theta and phi, and you already know what the result is. Okay, it's 4 pi, right? That's the angular integral gives, and that's why you have 4 pi r square as the volume of a sphere of radius r. It is this 4 pi. So you get 2 pi d equal to 2, so 2 plus 1, 3 over 2 over gamma 3 over 2. Okay, I will use another useful result which I can write here. Gamma of, let me write this way, z gamma z is gamma z plus 1. Okay, if you want to increase the argument of gamma by 1, you multiply it with z. Okay, with the same argument. That is what gives you gamma z plus 1. So let's use that. So this is 2 root pi into pi, that is pi 3 halves, over gamma 3 half is gamma 1 plus half. This is half gamma half, right? Half gamma half because of this property. So you have half gamma half. Now gamma half is root of pi. Okay, so also let me keep it here. So what do we get? We get here 2 root pi into pi over half, gamma half is root pi, that cancels, and this is 4 pi. Okay, which is what we expected. So it means that the formula that we have found is correct, and integral d omega d minus 1 is equal to 2 pi, d I should replace by d minus 1, So that kills that 1, and I have d over 2 over gamma d over 2. Okay, good. So now I will substitute all these expressions. So integral d omega d minus 1 from here, and where is it? Yeah, and this expression of this rho integral, which is here given in this form, and these factors. Okay, so this one, using this formula, gives you gamma of n minus d over 2 over gamma n. Now I will substitute all these things here and get the following. I d n m, let me record the entire thing here for later use, 2 pi power d 1 over minus k e square minus m square power n, and this is equal to minus 1 power n did I change the result? Yeah, minus 1 times 1 over 4 pi power d over 2 times m square power d over 2 minus capital N. Then you have gamma of n minus d over 2 divided by gamma n. Okay, so that's the result, but this is in Euclidean space. If you are looking at one loop, then you have 1 power of d, you have one time component dk0, and that will bring a factor of I. So you will have a factor of I if this expression was written in the Euclidean space, in the Minkowskian space. Okay, but let's keep the Euclidean. So now you see that the conclusion is that Feynman integrals can be continued analytically to complex d, okay, complex dimensions or complex, I mean, we used to call it small n earlier, but now I'm calling it d. Okay, so this is good. So 2 things achieved. One, that I can write it as a expression in d, and now you see that the singularities are contained in these gamma functions. Okay, all the singularities are contained in here. D is acting as a regulator, so that you don't have a naked divergence sitting here. It's not just I have infinity, but it's regulated. Okay, and that singularity I can recover by going close to d equal to 4. Okay, so this is a good situation we are in. At least we can regulate the integral, but this doesn't solve any of our problems, because at the end I should take d equal to 4 and everything is divergent. And next thing is to learn how to remove the infinities. Okay, we'll see that in the next video.